Welcome to Tic-Tac-Toe the Hard Way, the podcast in which a writer and a software engineer train an AI to play a simple game.
And take a hands-on approach to exploring the very human choices that go into training a machine learning system.
Hello, and welcome back to the podcast, the showdown, as it were.
This is it. This is where it all comes together, at least for the very initial trial.
In a small way. I think I've been thinking of this as the small game. The big game comes later. This is the small game.
I feel like I have a lot on the line here. I have to say I'm very, very invested. Very invested. This is like Super Bowl for me. Fortunately, I don't care about Super Bowl.
But you have this, so that's great.
And what is the this? What are we doing today?
So we have successfully come to the point where we each have an agent that can play tic-tac-toe pretty well against a random player, one that makes random moves. We can both beat that player. And today, we're going to pit our two agents against each other in the arena of tic-tac-toe and just see how they do.
What do I win?
You win the knowledge of
I'm gonna stop you
and
right there.
understanding. Okay.
And so just as a quick reminder,
I have no prizes.
What's the difference between these two agents?
The primary difference is how they've been trained. Yours has been trained using supervised learning, which is essentially teaching by example. And mine has been trained using reinforcement learning, where it sort of learns by exploration and trial and error.
So in training my model, giving it good examples, I did a fair bit of experimentation about which sorts of examples will train it successfully. Mm-hmm. And we agreed from the beginning that if I'm going to train a system, a model on boards, which is what we're doing, see a board and it's going to try to figure out what is the most likely best move to make, the move most likely to bring it to a win. Then, how many boards we use and some of the parameters around that is a matter of judgment and experimentation. And those boards were just completely randomly generated, all of the boards. Mm-hmm. And it actually trained surprisingly well.
Yeah.
Out of 500 games, it was winning 420 of them if it went first, which is an advantage, of course.
What was its overall win rate, sort of either first or second? Remind us what that was. I think it was around 80%.
We'll say that's right. I think that's right, yeah.
Okay.
I think it was 84%.
Cool. That's great. It's doing pretty well.
Well, I like to think so.
Yeah. And as we talked about last time, I trained a reinforcement learning agent, and it was able to win against the random agent about 90% of the time. Small difference when playing against a random agent.
You're very magnanimous. You crushed me.
But more interestingly,
can you just remind everybody reinforcement learning?
Reinforcement learning is the one where we sort of have an agent exploring the world. It gets to make actions. In this case, it's going to make tic-tac-toe moves. And the world gives it a reward. That can be positive, negative, or nothing. And typically here, it gets a reward at the end of the game. Did it win? Did it lose? Did it get disqualified? And it has to learn from that how to play the sequence of the game.
Which are the moves that get rewarded and to prefer?
Because it's trying to maximize long-term positive reward.
And just to be completely clear, the world that it's in is a very constrained world of sort of X's and O's or whatever, however you represent
just
them.
a tic-tac-toe board.
Yeah.
That's the entire world. So that's where I was last time, and today we're going to see how they play against each other. But I have a little bit of a story in between to sort of set this up. I had to put our agents in the same place so that they could play each other. And I ran it, and I noticed something, and it was that my agent, when going second, lost to your agent 100% of the time.
Let's just stop right there.
100%.
Really?
Yeah.
That is unexpected.
Shocking. In tic-tac-toe, you'd think it would at least get something just by luck.
Yeah, people do go second, and they do occasionally win.
Yes.
Going first, it's a substantial advantage.
But it's not absolute. Even random agents win going second a bunch. There's two things it made me observe. One, your agent is definitely playing better than random. It is not just a random agent. If it were playing randomly, I would have won some of those games.
Makes sense.
But then I was like, why is it losing 100% of the time? Something must be wrong in my training setup. And indeed there was. I had forgotten to turn on the thing where during training, it occasionally goes second or plays a different symbol. So at least in the reinforcement learning case, that player order was relevant. So I just had it set, and it was always playing first. And I guess a random agent was just bad enough that was fine, and it won. But when playing against a better opponent, could not do anything. Going second. Going first, it's still one reasonable numbers of times. So I had to go back and retrain my agent to play second occasionally. So in the retrained version, it just randomizes the order, whether it's going first or second. It also randomizes whether it's playing as X or O. And I retrained it, and now we can see how it did. So are you ready?
No.
Ooh, it's going to happen anyway.
No, it's not going to. If I can run out the clock on this, I'll be fine.
I'm next to the computer, so that's going to
I
solve
have a
that
question
problem.
for you.
Okay.
We can talk about this after or before, but I'm interested in what happens when one of the models gets the input, either from a human player or from a random agent or from the other person's agent, that here's the board and here's the move I'm making. We're playing, your agent says, oh, box number 4, that's the one for me. That goes into a model. It's going to go into my model in this case, right? My model is going to output something based upon
The state of the board.
state of the board and the neural network. A little tiny neural network, right?
Yeah.
Which has a set of weights and connections and stuff like that. So a board with the 4th square now occupied by your player, because that's the current board state, goes into my neural network. And what comes out?
So what comes out of that is the move that your agent should make.
In theory, there are 9 possible moves.
Yep.
Some of those are illegal because they're already occupied. Do we get a one-hot array back?
Well, so the way we set up the viewer thing is there's this function called move, and you get a board state, and you're supposed to return a position that you play. That's pretty much it. How you do that internally is sort of up to each model.
I want to take one step back from a 4 comes out of that function. You'll correct me, of course.
Yeah.
That function runs the input through the model.
Through the model.
And what comes back are actually 9 possibilities?
Yeah, a probability distribution over the 9 sort of boxes on the board.
And the boxes that already have a mark in them, so they're not legal, presumably they come back as either
They should have low probability if your model has trained well.
low probability or 0.
That depends on how well your model is trained. Things rarely go exactly to 0, so it should be ideally 0. 0 would be great. 0 would be best.
Okay, so within this function, 9 possibilities, each square has its own prediction, its own probability, and the function will pick the one that has the highest.
Yeah.
Okay.
So I believe looking at the code for your agent, it picks the one with the highest. My agent picks according to that probability distribution. So most of the time, it will pick the one with the highest, and with very low probability, it will pick the other ones according to those probabilities that came out. Most of the time, it generally tries to pick a good move according to that probability distribution. So if a probability of one of those boxes is 0, it will never pick that. If it's 90%, it will pick that 90% of the time. And some that might be 10%, 10% of the time it will pick that.
Is that an advantage?
I don't know. It just brings in more variety. I guess technically it can occasionally pick a worse move, but it means it doesn't always play the same game given the same board. So is that advantageous? I don't know, but I thought it was interesting.
There's only one best move. I'm not sure that's true.
Like at the beginning of the game, there's actually a whole bunch of reasonable moves. So it gives it more freedom to pick from that.
Okay, so just so I'm sure I'm understanding this, because of the way that I trained it, when it sees a board, a particular board, it will always pick the same move as the recommended one, the move to play. That's not the case for yours.
That's not because of how you trained it. In the agent, when you get the probabilities, you pick the highest one. You could have picked one of the top 3. You could have randomly picked between the top 2. So that's just more after you get the result from the model, how do you use its output? You picked the optimal strategy, which is pick the best move. I just wanted to experiment with like, oh, what happens if you occasionally pick a different move?
You know the difference between us? I wanted to win.
But I do think it's interesting for introducing variety, sort of particularly, let's say, at the start of the game. For an empty board, if you always pick the best quote-unquote move that your model has learned, it will always start in the same place. That might be great, but maybe there's other places to start, and I wanted to sort of allow for that possibility. Like picking a corner versus picking the center, or which corner to pick. I just give it that flexibility.
So if you were designing a commercial tic-tac-toe game and you're using machine learning for doing so, which would be your first error,
Yes.
it might well be the case that humans would figure out too quickly that every opening board you play square root number 3 and
Yeah.
recognize. Yeah. So
Yeah.
you're actually playing a little bit more like a human.
Trying
You're
to be a little
confounding.
tricky.
A little tricky. Okay.
Oh.
Have I stalled enough?
I
to
think
watch
you
my
have.
humiliation?
I think it's time.
We should allow the listeners to place bets on this before we. You might want to
If
pause.
that is legal in your state or country, go ahead.
Yeah, probably not.
Ready?
Define ready.
It's happening.
Okay.
So we're loading up the viewer and sort of watching the games progress.
We're seeing games flash on the screen and
Yeah.
lots of X's and O's, and I can't see any of the results. I'm too far away. What number of
Okay.
game are we up to?
We are going to play 500 games. And hold on a second. I'm just going to zoom in so that we can see the results.
Okay.
Better?
It's better.
Okay. Oh, I think it's done.
You know, I think we should play again.
Again? I think we should report these results and we'll let it run.
No, I don't think there's any need to report these results.
I'm going to say them because
I
they're
really
favorable
don't think
for me.
there are.
My win rate is 69%. And David's is 30%. So I do lose
31%.
occasionally. Yeah, you're right. 30.8.
Yep.
Very precise. I'm going to run it again and we can talk about that and see if that changes.
Why? There's no need to run it again.
I like to. You never know. Sometimes you got to run an experiment a few times just to confirm that it's real.
Yeah, just
and
to
I want to
grind your
confirm that
opponent
this
down
is
into
real.
the dust.
I wanna
No, I
confirm
see
that
where you're
this is
going.
real.
This is a side of you I did not expect to see, Yannick.
This is my only. This may be my only victory. You may have the game of Tic-Tac-Toe rigged. You may know some advanced strategy about the game that you invented.
Yeah, I'm sorry. Who wrote this agent playing software?
I did.
Okay.
But you wrote the agent, so there you go.
Oh, that is very true. Oh, that is a good tip.
And you'll notice particularly.
I'm edging up here. Now I'm up to 32.
Yeah, 32% and
Went up
67.
0.2.
So it's not like never winning.
You know what it's like? It's like
third or more
random.
of the
I think
time.
that's like random.
No, you did better, much better than random. At least, so I'll say this: my agent was beating random 90% of the time.
So now it's only
beating
me
yours
68.
about 67 to 70% of the time. So you are better than random for sure.
I am marginally better than random. So
quite a bit better than random.
no, don't make me
Take
feel
your
better.
wins as you get
No,
them.
no, I lost. I
we're-
lost. Oh my God, I don't know.
I will let you accept it. The first stage is acceptance.
Yeah, I'm not there.
Let's talk about what we're seeing because
Fine.
folks listen can't see.
I'm
so
seeing.
that was our overall win rate. The viewer also has statistics for how well we do in going first and going second.
No disqualifications. That is
No-
no
yeah.
illegal moves.
Yeah,
on
no
either-
illegal moves. This one,
for either of us.
'Cause
which
when
is
I had
sort
to-
of amazing, actually. I mean, it's a minor miracle.
it's pretty cool because neither of our agents has ever been encoded the rule as a rule that you cannot play on a move.
We
It's
just never gave it
purely
any-
through examples or rewards that it just knows that like that's not a thing to do. And this for me, like, yeah, I don't have disqualifications anymore. I think at this point, this agent has probably played like 30,000 games against a random agent. And I think that's fascinating. We've both used random data, but we're getting better than random results.
Yeah, one of us better. Than
Both
random,
of us
but-
significantly better than random.
make me feel
One of
bad.
us more significantly. So,
fine.
but I think that's really interesting for folks.
So we've trained these with different models.
Same model, different training techniques. Actually used the same model architecture
yes.
that you had.
Excellent point.
Unless you changed it in between the time I gave it to you. But
So if the number of nodes and connectors, all that stuff is the same for both of ours.
yeah, should be similar.
But the weights that connect them are different.
Yeah, exactly.
So we trained these differently
Mm-hmm.
for lots of reasons, including the fact that one of us is a very smart, experienced professional and the other does some JavaScript programming sometime. I would not want to draw any conclusions about which is the preferred technique for training a tic-tac-toe game, supervised learning or reinforcement learning. Okay, maybe we should.
I might draw that conclusion. But it sort of maybe leaves room for exploration as like how would one improve like a supervised learning approach? What are things that one can do there to make it comparable? Because like in some way, even in the reinforcement learning scheme, it does have to play these games to construct kind of examples it can learn from. It's just these examples are more encoded in terms of reward and stuff like that. So they're not exactly the same, but you know, I'm not saying supervised learning can't do as well. But it seems, at least in this instance, it hasn't. But this was just our starter project.
Yeah, but that's important to remember.
Why are we playing this in the first place?
Oh, you know, that's a really good point. We're playing this in the first place. We're using machine learning to train a system to play tic-tac-toe, which is not the way you'd want to go probably in real life, so that we can then see whether the basic approaches work in the simplest of cases.
Yeah.
So that we can then see if they're going to work.
In a more
possibly
complex
work.
case. Yeah,
in a more complex
exactly.
game.
I don't think our goal is to necessarily evaluate which learning scheme is the best. It's probably just to see how they do and sort of look at a couple of different approaches, and hopefully they each do decent enough.
In the high-stakes world of professional tic-tac-toe, there's room for more than one type of machine learning.
Unless Tic-Tac-Toe becomes the next major esport, we don't have to really worry about finding the best one. I was going to say, before we talk about Tic-Tac-Toe a bit more, I wanted to chat a little bit about sort of, given where we are now, what are some of the things we might have learned, or like our experience so far, what we might have learned that might be useful looking ahead? I have a couple of lessons for myself.
I'm just so humiliated now if I'm having trouble pulling it together to come up with a coherent answer. So why don't you go first?
Okay. I think we had talked a while back about whether the player order thing actually matters, or whether it's just going to learn it out of symmetry or something.
That is whether, in giving it data, whether I should be feeding in games where X goes first, X goes second, and likewise for O.
Yeah. And I can comment mainly on sort of, in my training approach, that like having the agent play second did matter, and that was useful, and it was a good thing to remember to do.
And I did do that ultimately, right? Yeah. Because my boards were any board in a game that won, no matter who started it.
Yeah, so yours got to see both sides as well.
Yeah.
Another thing that I think was really helpful is like speed of iteration is really sort of critical to being able to do lots of experiments. There was at a certain point, I'd first written it to be clearer but a bit slower, but each run was taking a long time. So speeding up the code just made it easier to try various things to see ultimately what worked best, and sort of trying experiments also sort of helps you find bugs. On that topic of bugs, debugging is hard. I also sort of ran into things. At least for me, regular day-to-day work, we had to have a lot of code review. When working by yourself, there's going to be some pain in the debugging. And with machine learning programming, it's even more so, because some of that is in your code and some of that is just what happened in this training process. And do you just need to train longer or adjust some hyperparameter? So it can be tricky to debug. So you may need some persistence, and persistence might pay off.
Most of my debugging was in just standard, dumb JavaScript mistakes, getting a variable wrong or whatever. That was frustrating. Some of it was errors that were so hard to find because they were so, I don't want to say dumb, but for example, we talked about the one hot array mistake that I made, where it turns out it does matter which order you put them.
But it was subtle. The error didn't like make things fail. It just played poorly.
Yes, yeah. And I don't think I would ever have spotted that unless you did, because I didn't know that it was wrong. I had a wrong assumption about it.
Even when I sat down with you, we just sort of we just started going through the code line by line and sort of trying to trace like what is different from what should be the case. But
it took you a little while, but not a tremendous amount. And it's a collaborative process for at least some of us, and I suspect for you, even when you're not dealing with somebody with my level of skill. Yeah,
and programming larger systems often usually is collaborative.
I learned more than just a few things, because walking through this with you, this process is entirely educational for me. We had done a prior project. I had some sense of the steps involved, but I think the important lessons for me is learning not to trust my intuitions about how machine learning works or what's going to make it work better. I found that when training it on different numbers of moves and different configurations of the random games I was generating, I could never tell how well it's going to do. One thing that surprised me when training it on unique moves was the difficulty of trying to interpret what the results were, not when it was playing against an agent, but just in terms of how the accuracy and
the metrics,
validity, the metrics
sort of produced.
It's hard to know what degree of accuracy would count as successful.
Yeah. So in the final thing, and those metrics are proxies for your final task. So that is something you have to build up. Nice.
I still say these systems are weird. They're doing something that sounds human and cognitive, like playing a game or whatever, which is sort of low level. But obviously, these are being used for all sorts of stuff that does some cognitive tasks better. And I think a common, especially because people call them neural networks, which sound like brain, they work like brains and the like. These systems are so counterintuitive, unintuitive in how they work. They're just not parsing through the data the way that we humans do, at least when we're thinking about it. How the brain does it is a different question, but it's a different way of, and here comes some air quotes, invisible at podcast air quotes. It doesn't think like us.
Interesting. Shall we talk about what lies ahead? The road to come, the road to Tic-Tac-Toe.
Vengeance. That's what lies ahead. Vengeance.
Your opportunity for vindication in this situation that you've given us. So I think it's great that we have a baseline. We know that we can train these agents to play these games in these two schemes. We know the pipeline that we need to do that. We have the pieces in place. So it's just sort of returning and saying, like, how do we now adapt this to a different game? And what do you suppose are the sort of the main building blocks in your case?
So I think they're exactly the same as they were for the Tic-Tac-Toe model, which is exactly the point of doing the Tic-Tac-Toe model.
Yeah.
So I want to generate games. I don't know how many, but we'll have to experiment. The experiments will take longer because you'll be training a system on presumably more games. It's a more complex game. Let me remind people what the Tic-Tac-Toe is, though, or just really quickly. So it's Tic-Tac-Toe, same board, X and an O. You win the same way by owning a row, any of the 8 possible rows. What's different is that in order for you to own a square, you have to have 2 of your pieces in it. Second thing is, in order to introduce some more randomness, at any point during a game, a player may once, but only once, play 2 pieces in one move. And those 2 pieces could both go into a square to take ownership immediately, or you might spread it across 2 squares. So I think that my steps are basically the same, which is to write a game generator that will generate random games that follow the new rules, and then try training a system on the games that get generated and go through the experimentation, which will be different, I presume, this time. But the same sorts of things, the results may well be different. Different parameters, et cetera. And see if it trains.
That makes perfect sense. I think another thing to keep in mind, you will have to change your model slightly because the data representation of what's coming in will be a bit different because the board will have more stuff in it. So you just have to adjust that first layer in your network to sort of take the expanded representation of a board state.
So instead of the input being 9 numbers representing the state of 9 squares on the board, each square can have up to 3 marks in it. So presumably it's going to be 27.
Yeah, something like that, exactly. So that data representation is going to change just because the game has changed. And that's how the model's going to learn the game. For me, very similar transformation. The environment is now going to be a Tic-Tac-Toe game instead of a Tic-Tac-Toe game. And the agent will still sort of interact with that. So it does need to be able to take in that board representation and make moves. We'll still need this random opponent that it can play against that can still play this Tic-Tac-Toe game. And we'll see how it does.
The environment you built, it's very nice, by the way, to use and to look at, into which we each loaded a model today, that we're going to have to change a little bit.
I'm going to have to make a new viewer.
New viewer, and a little change maybe in the get a move routine.
Well, the structure that will be the same. It's just the representation of the board state will be different.
Going in. So it's going to be something like 27 going in, and still coming out is going to be...
Now we'll need to decide. There will be like 1 or 2 numbers because we have to have a way to represent sometimes when you play 2 things. So we're going to have to adapt our data representation to be able to say, am I playing 1 square or 2 squares? And we're going to just have to see what that looks like in code.
You could also just sometimes have X go twice in a row. I'll leave this to you.
I don't, because a play is there's an actual play where an agent at some point has to decide to play 2 symbols. I think that is 1 play.
Okay.
As opposed to 2 different moves. But those are the details we'll work out in code. Basically, those representations have to be uniform in your training thing and in just how the viewer works.
Okay, so next steps for me is to generate Tic-Tac-Toe games, which I think is going to be more complicated in sort of uninteresting ways and not having to do with machine learning. And your next step?
Is to build a random agent that can play this game that you invented.
And use that to train your reinforcement learning thing.
Yep. Awesome.
Okay.
I'm glad we've come this far.
I am only slightly humiliated.
And I look forward to the
But
real
I
challenge.
have been humiliated by the best, so.
You are welcome. All right, everybody.
Okay. So long.
You've been listening to Tic-Tac-Toe the Hard Way with your hosts, Yannick Asogba and David Weinberger. This is a production of Google Pair, with thanks to Rebecca Salois, Eric Johansson, mixer and editor Brian Gordon,
and the entire Pair team of developers, researchers, designers, artists, philosophers, and more. A special thanks to Nikhil Thorat, who created the music with help from AI by Google Magenta.
You can find links to code and more in the show notes and at our website, pair.withgoogle.com/thehardway. Once again, that's pair.withgoogle.com/thehardway.